Okay, so I'm gonna go over the questions that I did regarding the DFA, or basically finite automata, for the people that couldn't come to the live meetings. So I think I did like 6 or 7 questions. So I'm just gonna go over them. So the first question stated that a DFA and NFA possess the equivalent capabilities, which we all know. So this question asks us to convert this NFA to a DFA, but it first asks us to state the difference between them. So the main difference is that the NFA can handle empty transitions and can have multiple arrows transitioning on the same input, whereas a DFA cannot have that. It must be deterministic. We must know exactly where it is going on each input. And then to convert from an NFA to a DFA, well, we first have to find out how many, the maximum amount of states we have, which is just 2 to the amount of NFA states. So in the NFA, we had 6 states, so it's 2 to the 6. And then we have to handle the E closures. So if we can transition an empty to another state, those 2 states, we have to merge them. Technically, we have to merge them. So on Q0, we can either go to Q1 or Q3. So we have to merge these 3 states. Wherever you see Q0, we're actually talking about Q0, 1, or 3. Then for Q2, it has an empty transition to Q5. So where we see Q2, it could also be Q25 or Q5. And then Q4 to Q5 is also the same thing. Then we start at the start state for our transition function here. We start at the start state, which is now Q013 because we merged it. And then we say on a 0 from any one of these 3 states, right? 1, 3, 0, because we merged them. Where can we go on a 0? And the only place we go is Q2, which is now Q25. And then on a 1, only place we can go on a 1 is Q4, which is now Q45. And then we continue until we map every single state in the DFA. Note that some states will be merged. So we have new states. So we have 4 states now. Then our start state remains the same, and our set of final states are any states that were previously final states. So Q2 and Q5 were final. Any states that has Q2 or Q5 are now final states. Then we can draw the DFA. The question also asks us to minimize it as well. So to minimize it, we just map our states. We categorize them by final and non-final. And then we say, where do they go? Do they go to a non-final or do they stay at a final? And well, all of the states go to a final and cannot be separated. So all of the final states stay in the same place, so we can merge all of them and we only have one non-final, so it stays the same. So we end up with 2 states in the end. Moving on to the next question, I won't be so detailed anymore. This is just a DFA, so given the formal definition. So they gave us this DFA and they want the formal definition. Remember, DFA is a 5-tuple. You have the set of states, you have the alphabet, the transition table, the start state, and the final state. And there is no final state. That's why I have empty here. There is no final state in this diagram. Then the question also asks to give some strings that will not result in the error state. You just follow the arrows and just any string that doesn't end up at the error state is one that will accept in this case. And then how do you get to the error state? That's question 3. Well, you get to the error state by going from R and a 1, or once you get a 1, basically you go to the error state. So any string that ends in a 1 will be at the error state. Any string that ends in a 0 will not be at the error state, essentially, for this question. For this question now, which was on 2018-19, it's another one that asks for the formal definition of a DFA. So again, you give the set of states, the alphabet, you give the transition table, the start and final state. This time we do have a final state here, which is the double lines. So that's our final state. Why is it there? Then question 2 says, give 2 strings over the alphabet that greater than length 5 or greater than or equal to length 5 that the string would accept, that will end up back at Q2. So I just said, hey, let's get a million zeros and then get a 1 to transition to Q2. So that's what I did here. Or I just followed the lines. right? So we get a 0 at the beginning, or we get a 1, we go to Q2. We get another 1, we're now at Q2 again. We get a 0, we go to Q3, then we get a 1 to go back to Q2, and then we accept. And then for the strings that don't accept, I say, hey, let's just never leave the start state, or let's end up at Q3, right? So you get 3 zeros, stay at Q1, you get a 1 to Q2, or another 1 to stay at Q2, and then a 0 to move to Q3. And then it says describing informal English, it just means regular English, what the types of languages that M2 recognizes, and it says it accepts all binary strings that does not end with 1, 0. Right? So it either ends in a 1 or 1, 0. It cannot end in 00. That's what that means. Now, this question, which I originally didn't do originally, it says construct the state diagram for the finite automata. So it gives us it gives us the formal definition. So it gives us this thing right here that we've been asked to do this whole time. And then we need to draw the DFA for it. So I've already taken the time to draw it. So let's answer questions 2 to 7, 2 to 6. It says, what are the accept states? Now, the accept states here are in the final curly brackets here, which is just Q2 and Q3. So that is just Q2, Q3. That's our set of final states for this one. What is the alphabet of the language that M accepts? So the alphabet is always the second one. So it's AB. So the alphabet is just AB. Another way, if you actually get the DFA, you can just look at what's on these lines here. So you can see it's AB. Then question 4 says, is M3, that's the name of this thing, a DFA or a MFA? Now, after I've drawn it, it's quite easy to see if it's a DFA or NFA, right? We see B here and a B here again. That's quite non-deterministic. So it's the, let me get this. Oh, I think I merged it. Right, so it's an NFA, but then it also says justify your answer. And then M, I'm going to say, wait, spelling is bad. Okay, what's this? How's the spelling go? Is it separate? I might have to leave the spelling. Ooh, I can't. But what I'm basically saying is that it goes to different places on the same, you know, let me unmerge it because this is not good. Yeah, so it goes to different places on the same input. On a B, it can either go to Q1 or Q5. So that's quite non-deterministic. All right, then part 5. Hold on. Yeah, part 5 says give one string of length greater than 4 over the alphabet that it accepts. So we start one, if you ask this question, just go at the start state and then just follow the arrows. Right? So it will go B, A, B. So it can go B, A, B, but then that's only 3, so we need 4. So now we have to go B. So B, A, B, B. Let me do it here. Oh no, I have to follow the arrows. So B, A, B, B, A. Right? B, A, B, B, A. That's 5. Let me just write that down. B, A, B, B, A. That's one string that it would accept. And one string that it would reject is anyone that does not result in us being at a final state. So let's go again. So B and then A, but what if we never leave Q1? So what if we have B and then an infinite amount of A's? If you catch the drift, right? So that would not result in us being at an accept state. Let me just delete this. We don't need so many there.
Well, which paper are you going through right now?
Yeah, so this question is from um 2018-19. The question that I did first was from the first two questions were from 23-24. I put a little snippet of the paper that it's from above each question so that you can always just check that paper if you're working paper by paper. I kind of
And
working
these are
topic by topic. These are
and
all
these
on
are
deterministic finite automata, so DFA.
I did go through these like the first session too though. Just
Yeah,
a
man.
check.
So I work them up the first session. Yeah, so let me just explain them really.
Ah,
Yeah, man. So now we move on to the next question. I'm kind of moving kind of fast because it's not really that it's kind of repetitive. It's kind of the same thing. I mean, if you really understand it, I mean, these three things right here are the same question from the same paper as well, from the same papers. So this one now, this is the famous wolf, cabbage, and goat problem where you have the wolf, cabbage, and goat on one side of the river. You need to bring them to the other side. So they actually give us the DFA. I didn't like how it looks, so I kind of redraw it properly. So they ask us several questions. The first question they ask us is it an NFA? Sorry, is it a DFA, a NFA only, both an NFA and a DFA, or neither a DFA or a NFA? And justify your answer. So I said it's only a DFA because I see there are no E transitions. You don't transition on an empty to anywhere. And every transition is unique, right? You don't have a G going to two places from any state. You don't have any one input going to different places from any state. And I also said that adding empty transitions for the sake of making it a DFA would also ruin the algorithm that they're trying to design as well. B says, give the formal description for P, including the transition table. So the formal description is all five. Remember, it's a five tuple, so you need a set of states, which I have here, which is just Q0 to Q10 plus the error state. You need your alphabet, which is WCNG, which is wolf, cabbage, goat, or nothing. The man does nothing. He brings nothing across with him. And then you have to do the transition table, which is just you mapping out each state and where it goes from each state. So we've taken the liberty of doing this live. And then the start state, which has the arrow up here, Q0, and then their final state, which is Q8 down here. QC says give the two shortest strings over the alphabet that P accepts. And the way I did this was I just start here at the start state, and I'll just follow the arrows until I reach the final state, the shortest possible path. And we actually had two of them of the same length, 7, that resulted in us accepting. Then we said, question D said, what are the sizes of the two shortest strings? And they were both 7. You can see the length of them were 7. Then it says, give any two strings greater than length 5 over the alphabet that result in P transition into the error state. So how I always do this, I would say, let's go to the first state, right? So we start here, we on a G go to Q1, and then we go back to Q0. So we'll never leave these two states. And anytime we get a W, we go straight to the error state. So that's what this first one here is for me. And then the next one was, let's say we were actually on the correct path, but then we got an invalid input. So we got to here, and then we got an invalid input, and we transitioned to the error state. So that's what that second one was. Then F says, describe in informal English the language that P recognizes. And it recognizes the order of moves that will result in all 4 characters safely reaching the other side of the river, because that's what the algorithm was for. That was it. That's what the question said in the beginning, right? You have the problem, the river problem, and you're trying to get all 4 to the other side safely, because the wolf will eat the goat and the goat will eat the cabbage, so you can't leave them together. So that's what this algorithm is designed to do. The order of moves that will result in them being on the other side, all 4 of them. Then it says, analyze the solution to the puzzle depicted by P and give a complete description of the solution, basically. So we know that one of these from C, we know that any one of these strings are accepted. So any one of these is technically a solution path. So I just pick the first one and describe it, right? So G means goat, N means nothing, C means cabbage, and W means wolf. So first, to start with the G, the man takes the goat to the other side. N, he comes back by himself. C, he takes the cabbage, and then so on, till finally he brings the goat over, and then all four of them are on the other side. I've shared the document, so you can just go through the document. The next question is another DFA question. So they give us a description of a problem, but this time they did not give us any state diagram. But they kind of give us in informal English what the transition function was from each state. So they kind of give us an informal description of this in the first couple lines. So the first question asks to design the state diagram. So I just used in English, I kept it in informal English to design what the states were. Based upon this, they said that it starts in the unoccupied position, and if it detects a person, it moves to the occupied position. Once a person is no longer detected, it moves to the flush position. Once flushing is complete, it moves to the refill position. And then once refill is complete, it moves back to the unoccupied position. That's what this text here says. And then that's the transition function that I needed to draw the state diagram. Question B says, give the formal description for the correct DFA, including the transition table. So yeah, you can just, I kind of use acronyms, I guess I can say for it, for the words, so that I can draw the table like this in a very concise manner. So I say instead of occupied, I have O, instead of unoccupied, I have U, and so on. And instead of having these words, I kind of just assign them binary values. Either the thing happened or it didn't, 1 or 0. And then you need a start state, which we also state remains the same, and the final state, which in machines like this, there is either no final state or the start state is the final state. And then I redrew the NFA, the DFA. It was a DFA. So I redrew it. Then it asks for some strings that they would accept. This is typical, right? Because the start is the final for me, I can accept nothing, or I can accept just strictly 0 based off of this DFA right here. Just basically following it. And then for D, it says give the extended transition function. I actually still don't know what it meant, but I kind of did some research and I'm thinking this is what it means, right? So if you look in the inner part where we have this, I have to merge it, where we have the U and the 1. But why do I have the U and the 1 there? I should, I know, because it's this. So that's the, okay, so the U is the start state, right? So U is the start state and 1 is the input at the start state. So we're at U and we get an input of 1. So this whole inner bracket becomes O. And then it becomes O and 0, which is this one. Sorry, O and 0, which now becomes F. So the secondary bracket becomes F. And then it becomes F and 1, which is here, goes to R, then it becomes R and 1, and then R and 1 and a 1 becomes U. So that's what this is. That's what the extended transition table was, from my understanding. And then the last one was give a string over the alphabet that will be rejected. So I just follow this path and just pick any order that did not involve me being at U. So any string that results in you not being at U will be rejected. Again, I provide this document so you can go over it in more detail. The last part of our regular expression, the last part of finite automata theory, I guess, is the regular expressions and the pumping lemma. So we start off with regular expressions here, where the question gives us a description. So it says, given the alphabet A, B, derive regular expressions for the following. So the language of all strings that start and end with the same symbol and can have any number of symbols in between. for all string W greater than of length 2, of course. So what that means is it starts and ends with the same symbol. So what that means is either I start with A, have anything in between, right? Have anything in between and end back with A. Obviously, this would be B. Understood? Or it starts and ends with B. Have anything in between and ends with B. So that's kind of what we did here for one, right? So we have the A right here. We start off with the A. Then we have the alphabet with a clean star, which means it can be 0 or more. And then we finish off with that A, but we also have to union it with the version that starts and ends with B, right? So it's either it starts with that A, has something or nothing in between and end with a A, or it start with a B and has something or nothing in between, then end back with a B again. That's for the first one. The second one is the language of all strings containing the substring BAB. Now this one is actually quite easy because it's just, so we use, instead of saying AUB, we just say sigma, which is just the alphabet symbol. So we said sigma clean star, which means 0 or more, BAB, sigma or more, sigma clean star, 0 or more, right? So you can either have BAB or it start with anything, or it start with anything, have BAB, end with anything or nothing. So you can also use that instead of saying AUB clean star in brackets. And the next question, which is part of the same, I don't know why I have this here twice. Let me delete that because it's the same here. Prove that the language A2 is not regular using the pumping lemma. So you have to use the pumping lemma for regular languages, which states that you have to select a pumping length. So you have a language right here. You first select a pumping length. Then you divide the string, your selected string that you want to pump into 3 parts, X, Y, and Z. Z is the remainder, but X and Y must be in the first P parts of your string. So let's say we have a string here. Let's say we have a string here of length, it's AB. So let me just do that. Of length 6, and we selected a pumping length of 3. What it means is that X and Y, the total length of X plus Y, must be within the first 3 characters of that string. And then obviously everything else, once you do that, everything else is Z by default. Y must not be empty. It must be at least 1. X and Z can be empty if need be. But in our case, we chose X to be empty for the sake of it. Y is 1, and then Z is the remainder, what we didn't select. I always think of it like that. But the laws of the language that we're using says that the number of A's and the number of B's must be the same as depicted by this A2 right here. So A to the N, B to the N. That means the number of them must be the same. So we start off with a string where they are the same, a valid string. So the number of them are 5. Then after we pump Y by 3, we see that we end up with 7 A's and 5 B's, which violates the language. Therefore, we have proven that it is not regular. If it was regular, no matter how many A's we pump here, the number of B's would also increase, which is not true. So therefore, it's not regular. But that's what should happen if it was a regular language. This next one is a theory-based question. So it says, explain the concept of pumping lemma regarding regular languages and its application in demonstrating a language's non-regularity. And then it also says utilize 2 regular languages, L1 and L2, to verify or refute whether the union constitutes a regular language. So just some theory. Again, we restate what the law. We restate what the laws are for regular languages. So the pumping lemma states that for any regular language L, there exists a number P, the pumping length, such that any string S in L, which is the language, with S, the length of S is greater than or equal to P, can be divided into 3 parts. S equals XYZ. So we just divide S into 3 parts, satisfying some conditions, right? The middle part Y is not empty, which is this condition that we have here. The length of X and Y is less than or equal to P, which basically is what I said. So the first 2 parts are within the first P characters. So if we pump 3, X and Y, must be within the first three characters. And then for all I greater than 0, once we pump it, it must still be a regular language. It must still be a regular language. Now, the application of this is that to prove that a language is not regular, we assume it is regular and satisfies the pumping lemma. Then we find a string that no matter how we split it, pumping it leads to a string that does not belong to the language, just causing a contradiction. So we use proof by contradiction to prove that a language, using the pumping lemma to prove that a language is not regular. And it's the same for context tree, it's just that the pumping lemma formula becomes different. Now the example with two languages. So we say let L1 be the language of all A's, and then L2 be the language of all B's. If we union them together, right? So it's a union where you put them together, so you join them together. So their union would be L1 union L2, which is the language of all A's plus the language of all B's. And we assume that they're both regular languages that can be described by finite automata. And we say that this is the set of all strings that consist entirely of A's or entirely of B's, which satisfies this. So we don't actually change what the original languages were. So we said that regular languages are closed under the union. Therefore, L1 union L2 is also regular. Right? Because it didn't actually change it. Right? It's not an interaction, it's not complement, it's the union, it's or. So it's either you have one regular language or the other regular language, not the interaction, which is a different situation. So that's the end of, I guess I can call it finite automata and regular expressions and pumping lemma. This is not the full theory, because I just got a picture of what the actual final exam is going to come on, and it's going to be 10 marks on finite automata theory. And I mean, right here, I only have one piece of theory, which is this, I guess, on pumping lemma. And I guess you could call this theory as well the difference between a DFA and an LFA, but I think everyone knows that already. I think we need to focus more for the final exam. This is on the first lecture, that is Chomsky's hierarchy of things. So you have to understand what are the different classes of languages, which I technically have here in this document here. Where is it? I have it here. So it's the different four models of computation that Chomsky recognizes. So the first one is finite automatas, which is type 3. The next one is the PDA, which is a type 2. The finite automata is used for regular languages. And sorry, the class of the language is the regular languages, and it's modeled by the finite automata, the DFA or the NFA, and it's a type 3 language. The next one is the context-free, type 2, and it's modeled by the push-down automata, PDA. The third one is context-sensitive, which we don't do in this course. The type 1, measured by the linear bounded automata, LBA. And the final one, which is what at least 50% of the final is going to be about, is the recursively enumerable languages, type 0, modeled by the Turing machine or register machine, considering that they are equivalent. And then the next thing, like I'm on this slide, is what's it called? Where is it? It's just this complexity. This is gonna be on the final for sure. But there's also going to be the calculation parts of it, which I don't have on this document. I might do a different document for it, but I'll definitely recommend and give this document here a read, because we're gonna have to know. Like, I saw this nasty question on 23, 24 last year this time, so I don't know if it's gonna come back again. It says describe the complexity class XP time, exponential time, NL, natural logarithmic time, polynomial, exponential space and time kind of different, but the same, they're related. NP, right? Non-deterministic polynomial time. P space, polynomial space, and polynomial space is different from polynomial time, right? So it asks us to describe them precisely, accurately, and give the definitions, and also show the hierarchical structure of all of these complexity classes. So I've taken the liberty of defining all of them and then given the relationship between them here. So I'm just gonna start with this over here. Problems for so the NL means non-deterministic logarithmic space. It's not time. It's not logarithmic time. It's logarithmic space, right? There's two things. There's space complexity and time complexity. Space complexity is how much memory an equivalent Turing machine would use to model a problem. And then the time complexity is how much time that equivalent Turing machine would need to run that problem, right? So a non-deterministic logarithmic space Turing machine would solve a problem with very little space in polynomial time. So it would use logarithmic space and solve it in polynomial time. A polynomial time Turing machine or a problem in polynomial time is efficiently verifiable in non-deterministic polynomial time, right? So non-deterministic polynomial time, you can check your solutions easily. You can verify it. In non-deterministic polynomial time, I'm stressing this by the way, they're easily verifiable. You can verify them in polynomial
Now
time.
interrupt you, but you have 3 minutes.
Yeah, I know. I can see it. I can see it. That's why I'm kind of stress some of these things. And then polynomial space is for again, for non-deterministic polynomial time, checking solutions can be done within polynomial space, right? That's memory for a non-deterministic polynomial time problem. And then for polynomial space, if you only use polynomial space, it can take at most exponential time. So to solve a non-deterministic polynomial time problem, it would take at most exponential time, if that makes sense, right? Because non-deterministic kind of bump it up. Then for exponential time problems, they are solvable within exponential space. And then exponential space are solvable in whatever comes after exponential thing after that time. But I think exponential space is the biggest one that we've done so far. But yeah, please, 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 please give this documentary. I mean, imagine if this come on the final. I'm sure everybody will have problems. So try and make it do some damage control. Because as far as I'm concerned, complexity is coming in terms of theory. The theory part of it is coming. So we should know all of that. And then the next one that we should know is NP versus P. So this entire one over here. So this one over here is dedicated to both. This one right here is dedicated just to NP and P. And also as well, this right here. This question right here is dedicated just to P and NP. It says contrast any two of the classes that we studied. I just focus on the two that are most likely to come on the final. And again, the post correspondence problem, it brings us back again to P versus NP, which, yeah. And then the halting problem here is the full solution to the halting problem. So if you can just remember this, I mean, it's not that difficult. Just, key thing, only focus on what I technically have in color, because I kind of say I want it this to read, so you can only focus on what's in color. So for the halting problem, it's just, we're given a Turing machine M, so this is what the question asks. We're given a Turing machine M and an input W, and we need to find, does M eventually halt on W? Right? So then this is where we're going proof by contradiction. We first assume that it would halt. So yes, if it halts, no, if it doesn't halt. We then construct a new Turing machine that checks if M would halt, right? A new one H that checks if M would halt. And this one would now do the opposite. And then we feed it back its own input. And then based upon that, we would then result in a contradiction. Because if the inner one halts, the outer one doesn't halt. If the inner one doesn't halt, the outer one halts. That's how we solve the halting problem. I'm gonna have to stop it there, but you can read it. It's all here, and I provided this document. I did this in the morning, but I'm begging you to remember it because it's gonna come on the thing.
You
Yeah, but
can
that's it.
send it to the group.
I already sent it. But I guess this is the end of the meeting, guys. Again, time's up. I can go over this document another time as well, because this is very crucial and it's at the end. So I guess many people didn't really catch it.